Welcome back to Lecture 24. This is the fourth lecture video for Lecture 24. In this part 4, we're going to discuss the de Broglie wavelength. This takes us down to the second to last line of our equations, and let's discuss what this equation is telling us. So if we take a look, we have lambda, okay? This right here is the wavelength of a particle, okay? So this is particle wavelength. I will briefly say that although as an equation, this de Broglie wavelength is rather short and concise, the idea is large. And to not lose sight of that, I simply want to say that the particle wavelength is a statement that particles, like electrons and protons, behave as waves in a very similar way as photons behave as waves and particles as well. All right? So the wave-particle duality applies to everything, not just photons. All right? Now, the wavelength of a particle is equal to Planck's constant divided by the momentum of that particle. Okay? So in order for a particle to exhibit wave-like properties, where lambda is a measurable quantity or a quantity that has effects on other systems that physicists are interested in, you need to have a very small momentum. The particle needs to have a very small momentum because Planck's constant is to the order of -34. So if you want a wavelength, that's going to be on the order of, say, visible light, nanometers, 10 to the -9. That means that the momentum would have to be the difference, or 34 minus 9, which would give us 25. So our momentum would have to be on the order of 10 to the -25 Newton seconds. Okay? Because it's translational momentum, mass times velocity. That means that macroscopic objects that have momentum on the order of integer or millinewton seconds even, right, small, things like that would still have a immeasurably small wavelength, smaller than anything that's known to modern physics, smaller than the atomic nucleus, much smaller, okay? All right, so that's the idea, okay? This leads to things like electron diffraction, just like you can have wave diffraction through slits. So single slit, double slit, wave diffraction of electrons, much like we talked about in our physical optics chapter for light. Okay? All right, so I'll finish labeling things. I already said what they are, but this is translational momentum. Okay? I won't belabor the point by relabeling Planck's constant. We already know what that is. And then just here, this is just mass and velocity, but of course it is, because it's P equals mv, right? Okay. All right, so let's take a look at our examples. All right, so we'll move on past our examples of Compton scattering to our first example of electrons behaving like a wave. Okay. So, in this example, we are told that the wave nature of electrons is manifested in experiments where an electron beam interacts with the atoms on the surface of a solid. By studying the angular distribution of the diffracted electrons, one can indirectly measure the geometric arrangement of atoms. Assume that the electrons strike perpendicular to the surface of a solid and that their energy is low. This is the kinetic energy of the electrons, 100 electron volts. So they interact only with the surface layer of atoms. If the smallest angle at which a diffraction maximum occurs is at 24 degrees, what is the separation d between the atoms of the surface? Okay? So what we're looking at here is a problem that is essentially a wave interference problem. We're going to use the same math that we use for say a double slit, because we can have two sources if we think of the two reflected waves, so it's like two source interference. Of course, it's also very similar conceptually to the idea of thin film interference because the two sources are being reflected, right? Okay. So it's all just about path length difference, setting them equal to the wavelength, and going from there. Okay. So I do want to quickly summarize, since the concepts are important here. We are using the wave nature of electrons in our solution conceptually. Okay, which I suppose is mentioned in the body of the problem. We're going to have that the reflected beams and atomic spacing, we have two source interference pattern. Okay, so I'll just write two source interference pattern. Okay, that's the type of problem. So ultimately, there can kind of be a lot of categories of two source interference, and it's more useful, instead of saying, oh, is this more like thin film or is this more like double slit, just think, okay, well, they're waves. They can interfere constructively or destructively. They're going to interfere constructively if their waves are one full wavelength out of phase, or an integer multiple of a wavelength out of phase, and they're going to interfere destructively if the two waves are half wavelength out of phase, or an integer multiple of a half wavelength out of phase. Okay, so ultimately that's always the idea that will get you there. Okay, and so the formula that we're looking for, we're going to have d sine theta. That's the path length difference. All right, let's label that. Right, two sources, two waves with a path length difference of d sine theta. Real fast, so I don't make any assumptions here, this is coming from the geometry of this picture. It's simply a matter of that, right? Now, in order for this to be exactly d sine theta, we are making one of our famous predictions, one of our famous approximations. This is the parallel wave approximation. Okay? In this case, right, we still have, if these are truly, right, two waves, would they ever converge? Because they are separated, right? What's the amplitude of these waves? How much physical space does the amplitude take up, right? Well, that's a question for another day. This definitely, we can legitimately make a parallel ray approximation here. Okay, and so that path length difference is going to be equal to an integer m multiple of a full wavelength of our waves. Okay, these are electron waves, mind you. Right, fascinating. So why do I know that it's going to be an integer multiple of a wavelength and not half? Well, because I was told that I'm looking at constructive interference. There is it. Yep, that was at the very end. Yeah, so a maximum. Okay, so if we're talking about a maximum, that's constructive interference of our waves. Okay, so that means d, this is our atomic spacing, will just be m lambda divided by sine theta. Okay, and m is going to be 1 for the first maximum. Okay, so that will give us the baseline spacing. Okay, so then we want to find our wavelength. Okay, now we're given the wavelength, right? Well, no, we were given the kinetic energy. From the kinetic energy, we can find the velocity. From the velocity, we can find the momentum. From the momentum, we can find the wavelength. Although we can kind of skip the middle step. Okay, so we're going to use, and the kinetic energy, K, is equal to 1/2 mv squared. Okay, and so then V is going to be the square root of 2k over m, which will be equal to 100 electron volts, okay, converted over to joules, and this would be, I'll just make it 200, 200 electron volts times 1.602 times 10 to the negative 19, okay, and that's just going to be joules per electron volt. It's our conversion. And then we're going to be dividing by the mass of an electron, 9.11 times 10 to the negative 31 kilograms. Okay, so there we have it. Of course, our electron volts cancel out. We're left with joules or kilograms. It's going to give us meters per second. All right. So that ends up giving us, I'll go ahead and give it to you numerically, 5.93 times 10 to the 6 meters per second. Okay, so now we can go right to the wavelength. Okay, so the wavelength is going to be Planck's constant over mv. So here we have our 6.626 times 10 to the negative 34 joule seconds. All over our electron mass, 31 here, but kilograms of course, times the velocity we found, 5.93 times 10 to the 6 meters per second. Okay. Looks good. All right. So that works out to be 1.23 times 10 to the negative 10. 3 times 10 to the negative 10 meters. Aha. Okay. So what are we looking at here? Atomic spacing. Okay. So that gives us D. Ultimately, that's what we're looking for. It leads us right to D, right? Because we know D is going to be 1 times lambda over sine theta. Okay. Now sine 24 was what we're working with. That's going to change it a little bit. It's going to make it a larger value. Okay, so we'll just take the number we had, our lambda, and it's just going to be divided by sine theta. So it'll just be 1.23 times 10 to the negative 10 meters divided by sine of 24. And this would just be measured by some sort of detection screen, I imagine. And 3.01 times 10 to the negative 10 meters is our final spacing. All right? Now, it's a fairly realistic number. I think the solids are going to have spacing between them that are bigger than the atoms themselves, just due to the way kind of the bonds work. I mean, that's my understanding of these kind of metallic solids. But 10 to the negative 10, 1, or around that order, around 1 times 10 to the negative 10 is the atomic size in general. We'll see that when we talk about like Bohr radii. Obviously, some atoms are bigger than that. Things take up more space, especially big heavy atoms. Things bigger than iron, for example. Point being here that this scale, right, that's the wavelength scale of atoms. Okay. This is a pretty fast electron, right? Moving at 5.93 times 10 to the 6 meters per second. It's still, well, if you think about it, right? It's 2 orders of magnitude less than the speed of light. Slightly more than 3, so it's a little bit above 1% the speed of light. Is that relativistic? Not really. Maybe a tiny effect, okay? Again, rule of thumb is 10% or higher. If I ever ask you a question that would have relativity in it like this, maybe if we're dealing with some other sort of spacing scale, then I'd warn you. Okay, hopefully the approach makes sense. We found the atomic spacing through electron diffraction, through treating electrons like waves. Okay, realistic thing that happens with electrons, realistic way that they are used in applied sciences, applied physics, right? Okay, so let's take a look. What was the other one I wanted to show you? So we have, the Broglie wavelength of an electron with a kinetic energy of 120 electron volts. Okay, pretty straightforward. It's the same approach. It just doesn't involve the diffraction as a final step. So definitely leave that for your practice. Make sure you can kind of carry it through and it makes sense. It's good just to make sure you understand what all the variables are. Okay, so a non-relativistic free electron. Okay, if the wavelength of the electron doubles, its kinetic energy changes by what factor? Okay. All right. Yeah. All right. This is a good one to show you, and I think this should wrap it up. Yep. Yeah, because then we're just going to go into I'll leave 13 for further practice. Let's see, because it's just kind of got more of the same ideas, working with the Broglie wavelength and kinetic energy. So, but in that case, you're trying to actually find the voltage. So you're kind of working backwards. 13 is even more similar to 10, again minus the wave interference, but you're kind of working backwards to find the voltage that got you there. Okay, the acceleration voltage, as we'd call it. But let's take a look at example 12, okay? And this will conclude the video. All right, so here we're told there's some particle that has some initial kinetic energy. So we'll call that K naught, okay? And I've been using the E, so I'll drop it here. Okay, so initial kinetic energy, that's just going to be 1/2 mv squared. So what are we doing? Okay, well, we're going to, if the wavelength doubles, okay, well then how is the wavelength related to the kinetic energy? Okay, well, let's find the kinetic energy as a function of the wavelength. I'm just going to do a straightforward substitution where I replace V with everything that it's equal to based on the Broglie wavelength formula. Okay, so what would that look like? Well, I'd still have my 1/2 m, but my V would become h over m lambda, and that would still be squared. Okay, and where does that come from? Well, so you don't have to flip back to the key equations. This is again just from the Broglie wavelength, that lambda is h over mv. Okay, all I did was just solve for v, and then substitute it into the kinetic energy formula. I'll simplify this expression a bit, and it'll become Planck's constant squared, and then divided by 2m lambda squared. Okay? So now I simply want to see what happens when I double lambda. Okay. Thus, k, okay, this is the new k, will be h squared over 2m, but what am I going to do now? I'm going to replace lambda with 2 lambda, okay? This is the new lambda. 2 lambda equals lambda original, okay? And, excuse me, to be clear on that, let's label this lambda naught to match up with k naught, okay? Because it's the only thing that's changing. All right, so then we'll go ahead and deal with the fact that it's squared, which would give us a 4, right? So the 4 would come out, okay? So when we get, and if I just pull the 4 out to the front, I can clearly show that everything that's left, of course, is just k naught, because it would be just h squared over 2m lambda squared. So that means that we've, well, have 1/4 the original kinetic energy, okay? So it reduces by a factor of 4. Okay, we divide the kinetic energy by 4 when we double the wavelength. There is a, what do we call that? An inverse square relationship between the two. Just like between the Coulomb force and distance. Oh, interesting stuff. Okay? Okay, so that concludes our portion of this lecture. That's video 4, covering the de Broglie wavelength. Please take a look at the final lecture video for this lecture. That'll be part 5, where I talk about Heisenberg's uncertainty principle. Thank you for watching.